Hey there, science fans. Today we're diving into the fascinating world of automata theory. Imagine machines that think, well, sort of. Automata theory is all about abstract machines and how they solve problems. These machines, called automata, follow a set of rules to process information. They're like tiny computers with a specific purpose. One type of automaton is the finite automaton, or FA for short. FAs are like the building blocks of computation. They help us understand how computers process information at a fundamental level. Plus, they have tons of real-world applications. From checking if your password meets the requirements to powering the search function in your web browser, FAs are everywhere. In this wild ride through the world of automata, we'll unravel the secrets of these computational wonders and see how they shape our digital lives. Get ready to expand your mind, because things are about to get fascinating. Let's get down to business and formally define what a finite automaton really is. Picture this. A finite automaton is like a map with different states and arrows connecting them. These states represent the different stages of processing information, and the arrows show how the automaton moves from one state to another based on the input it receives. We can represent a finite automaton using a fancy 5-tuple formula M equals Q sigma delta Q0F. Don't worry, it's not as complicated as it looks. Let's break it down. Q represents the set of all possible states our automaton can be in. Sigma is like our alphabet. It contains all the symbols our automaton can recognize. Now, delta is the heart of the automaton. It's a function that tells us which state to move to based on the current state and the input symbol. Think of it as the rulebook for our automaton. Q0 is our home base. It's the initial state where the automaton starts. Lastly, F represents the set of final states which tell us if the automaton successfully processed the input. So there you have it. A finite automaton is like a tiny machine with a set of states, an alphabet of symbols, a transition function, a starting state, and a set of final states. It's a simple yet powerful concept that forms the foundation of computer science. Now that we've got the formal definition down, let's find out how to visualize these fascinating finite automata. One way is by using something called a transition diagram. Imagine a bunch of circles representing states and arrows connecting them representing transitions. Each arrow is labeled with the input symbol that triggers that transition. Transition diagrams are super helpful because they give us a clear picture of how the automaton processes information. We can trace the path from the initial state to a final state based on the input, making it easy to see how the automaton makes decisions. Another way to visualize finite automata is by using transition tables. These tables list all the states and input symbols, and the entries show the corresponding transitions. It's like a spreadsheet for our automaton. Whether we prefer the visual appeal of transition diagrams or the organized structure of transition tables, these representations help us understand and analyze the behavior of finite automata. It's like having X-ray vision into the world of computation. Hold on tight, because we're about to explore two main flavors of finite automata: deterministic and non-deterministic. A deterministic finite automaton, or DFA, is like a well-behaved robot. For each state and input symbol, there's only one possible transition. It's like following a set of clear instructions with no room for ambiguity. On the other hand, a non-deterministic finite automaton, or NFA, is like a free-spirited artist. It can have multiple possible transitions for the same state and input symbol. It's like having the freedom to choose from different paths, leading to a world of possibilities. The cool thing about NFAs is that they can be more expressive than DFAs. They can represent certain languages more concisely, even though they might seem a bit more complex at first glance. But don't worry, both DFAs and NFAs have their strengths and weaknesses, and they both play crucial roles in the grand scheme of computer science. So there you have it. DFAs and NFAs are two sides of the same coin, each offering a unique perspective on the power and flexibility of finite automata. Section 5. Applications of finite automata. Now that we've explored the ins and outs of finite automata, let's dive into the real world and discover their incredible applications. These computational wonders are everywhere, quietly working behind the scenes to make our lives easier. One of the coolest applications is in digital circuits. Remember those DFAs we talked about? They're perfect for designing sequential circuits, which are the backbone of computers and other digital devices. These circuits remember past inputs and use that information to determine their output, just like our trusty DFAs. Another important application is in lexical analysis, which is a crucial step in compiler design. Compilers are like translators for computer programs, and lexical analysis is like breaking down a sentence into individual words. FAs are used to build lexical analyzers, which identify and categorize these words or tokens in a program. But wait, there's more. FAs also power string searching algorithms, which are used everywhere, from searching for text in a document to finding a specific gene sequence in a DNA database. They're also essential in communication protocols, ensuring that data is transmitted reliably between devices. From the tiniest microchip to the vast networks that connect our world, finite automata are the unsung heroes of the digital age. Section 6, examples of DFA and NFA. Let's roll up our sleeves and get our hands dirty with some concrete examples of DFA and NFA in action. Imagine we want to build an automaton that recognizes the language of all strings containing the substring AB. For a DFA, we'd start with an initial state and then have transitions for each input symbol, A or B. If we encounter an A followed by a B, we transition to a final state. Otherwise, we stay in non-final states. It's like following a treasure map, where AB is the hidden treasure. Now, for an NFA, we can be a bit more creative. We can have multiple paths leading to the final state, representing different ways to find the AB substring. It's like having multiple trails leading to the same mountain peak, each offering a unique adventure. By working through these examples, we can see how DFAs and NFAs differ in their approach to language recognition. DFAs are like meticulous planners, while NFAs are more adaptable and can explore multiple possibilities simultaneously. Section 7, the power of regular expressions. Hold on to your hats because we're about to unlock even more computational power with regular expressions. Regular expressions, or regex for short, are like superpowers for pattern matching. They allow us to define complex patterns using a concise syntax. The best part is, every regular expression can be converted into an equivalent finite automaton. That means we can use the power of FAs to search for patterns in text, validate data, and even perform complex text manipulations. Think of regular expressions as a secret code that unlocks a whole new level of computational flexibility. They're like wildcards on steroids, allowing us to match any character, a specific number of repetitions, or even choose between different patterns. With regular expressions in our toolkit, we can unleash the full potential of finite automata and tackle even the most challenging pattern-matching tasks. It's like having a team of microscopic codebreakers at our fingertips. Section 8, limitations of finite automata. Now, before we get too carried away with the awesomeness of finite automata, let's take a step back and acknowledge their limitations. As incredible as they are, FAs have their boundaries. One major limitation is that finite automata have limited memory. They can only remember a finite amount of information represented by their states. This means they can't handle tasks that require unbounded memory, like recognizing languages with infinitely many patterns. Another limitation is that FAs can't handle nested structures like matching parentheses or tags in a markup language. They're great at processing linear sequences, but struggle with hierarchical relationships. Despite these limitations, finite automata are still incredibly powerful tools for a wide range of applications. By understanding their strengths and weaknesses, we can use them effectively and appreciate their elegance and versatility. As Section 9, conclusion, automata's enduring significance. As we reach the end of our automata adventure, it's clear that these computational wonders have left an undeniable mark on the world of computer science. From the theoretical foundations to practical applications, finite automata have shaped the way we interact with technology. Their ability to recognize patterns, process information, and make decisions based on a set of rules has revolutionized fields like compiler design, digital circuits, and communication protocols. And let's not forget the power of regular expressions, which amplifies the capabilities of finite automata to new heights. As we continue to push the boundaries of computation, Finite automata will undoubtedly remain essential tools in our arsenal. Their elegance, simplicity, and versatility continue to inspire new generations of computer scientists and engineers. So there you have it, folks. Finite automata, the unsung heroes of the digital age, silently shaping our world one state transition at a time. Keep exploring, keep questioning, and never stop marveling at the wonders of computation.